Next up, we have Aaron Courville. Aaron is also a professor at the University of Montreal, a CFAR chair, as of recently the scientific director of Ivado.
That's right.
And literally wrote the book on deep learning, so probably don't need to say too much more about his background. But also going to be talking about today learning to cooperate in multi-agent social interactions. So.
Right, thank you. Yeah, so I don't know if this has been too much built up. I don't know if I might, there's a risk that I'm going to disappoint you in terms of the scale of the problems we're going to take on, but let's see. One thing, yeah, so as Jacob mentioned, I am the relatively recent scientific director of Ivado, which is the organizing group that brought us together today and the last few days. So if you have any questions about Ivado, feel free to come to me and I will confidently direct you to somebody who actually might know an answer for you. Okay, so yeah, so we're going to be talking about learning to cooperate. And I think Gauthier's presentation nicely set me up for a lot of the things we'll be discussing. This is the slide I usually start with, and I am starting with it here. But of course, with this group, I think it's pretty uncontroversial that we are living in a world where we're concerned about agents, and we're seeing a case where agents are being developed, actively being developed by maybe even people that are here and participating in this workshop. And we've already discussed that it doesn't take that much imagination to imagine that once we have agents in the world, and LLM-based agents in particular, that they're going to go out into the world and start interacting with one another, right? We're going to have agents who are representing perhaps us as clients interacting with other agents who represent other people, other companies, and my preoccupation has been along the lines of what does that mean? What are the implications for that process? And mostly around the idea that there isn't very much attention being paid to the nature of that interaction. Now, there is some work, especially recently in the last year, there's been work developing, sort of laying the groundwork. For example, I think this is Google put out this A-to-A protocol, which is essentially like MCP, but for agent-to-agent interaction. So this is establishing a mechanism for which agents can interact. I will say, though, that this kind of interaction looks a little bit closer to the kind of tool use interaction you'd expect to see in a system where there's kind of complicated agents that are sort of shoving jobs to other things that they're calling agents. This isn't really the kind of agent interaction I'm envisioning here. So I'm really looking at the kind of case where I just described, where you have an agent that represents you interacting with another agent that's representing another entity. And the key difference between this sort of vision of multi-agent and the kind of vision that I'm describing and sort of preoccupied with is this notion of the incentives, right? I'm interested in cases where the two agents don't necessarily share the same incentives, or at the very least that their incentive structure and maybe the way in which their policies are established are not sort of universally linked. Right? I'll get a little bit more into that as I go along. So this is actually something that Gauthier brought up as well. We're both concerned with some of the risks involved in this multi-agent interaction. In particular, he's sort of more interested in number 3. At least he was talking today was more interested in number 3. I'm going to be talking today about the 2, which actually is also work with Gauthier. So I guess you're also interested in this context as well. But yeah, so this is, by the way, a really nice survey. If you're interested in this area at all, I really recommend it. It's got a great sort of lay of the land of all of these kinds of different risks, and a tremendous number of works cited in there. The other thing I want to bring up, when we talk about risk, the alignment problem often comes up. And to a certain degree, when we talk about training these algorithms, we're always thinking about the alignment problem. I want to sort of point out, this is typically how people think about in the AI safety community, especially people that are concerned with catastrophic risk. This is how they view the alignment problem, right? It's sort of something you're kind of squinting at. You have humanity, and we're worried about AI aligning to sort of humanity's interests. From a multi-agent point of view, this doesn't seem very realistic to me. The view that I like, and what I would say is well described in this paper here, first author Joel Leibo, who actually gave a talk this summer in our multi-agent Ivado group, is what they call, and what I've sort of by shorthand called the polychrome quilt idea, where this is really envisions a world where there are many different interests, so many different human interests, and potentially many different agents with their own interests. And the emphasis isn't on achieving some perfect alignment that we are not really able, we know already that we're not going to be able to achieve this perfect alignment. It's more about establishing a notion of how do we sort of align sufficiently that we can kind of get, that our behaviors are at least compatible with one another and we can sort of get along, right? This is actually kind of how society functions anyway, right? We don't have to align on perfect beliefs among ourselves. We just have to align sufficiently that we can kind of establish norms of behavior in our society and move forward on that basis. So this would be kind of an approach that I would advocate, and I think our work is attempting to move in this direction as we go forward. All right, so when we talk about agents, you know, to me anyway, as a sort of a maybe an older school, not slightly, well, it's funny to say old school deep learning, but I guess that's kind of how I feel I am these days. I think when I think of agents, I think of the natural framework for training agents as being reinforcement learning. And so, by the way, there's also, when it comes to agents and establishing a definition of agents, to me, what an agent is an entity that interacts with the world, takes actions in the world, and possibly influences the world through their actions. Right, that's it. I don't need to invoke tools or something like that, which is something I've heard come up as a definition of agents in the context of LLMs. I think that's unnecessary. I'm really relying on sort of the old-fashioned reinforcement learning definition of agents. So when I think about agents and when I talk about agents, that's really what I'm talking about here. So everything I'm going to be talking about here doesn't just apply to LLMs, but as far as I'm concerned, certainly does apply to LLMs. And the second part of the talk, we'll get into our work in LLMs in this case. But yeah, so getting into the framework that we have here, so we have our agent, which is going to be characterizing a policy. Oh, you don't see that. Okay, let's see. We'll use this. So we have our agent characterized by a policy. It takes actions in an environment, and then that environment emits observations. We can think about observations or we can think about states. I think moving forward, we're going to be talking about states. For our purposes, these are the same thing. In reality, of course, the state is sort of something that's potentially not entirely completely observable to the agent, and the agent only sees some subset or some projection of the state, which is the observation. For our purposes, we're going to assume that the state is completely observable. If you're interested in that question, we can talk about it later. But for the most part, the state and observation are equivalent. And we get some reward. And of course, in the reinforcement learning framework, the point of the agent or its goal is to determine what is the right policy or mapping from observations or states to actions that maximizes its reward. Right. Of course, we're talking about multi-agents in this talk, in this session. And so we, of course, have more than one agent in the environment, right? So we have our two agents here. And for the most part, today, I'm going to be talking about two-agent interaction. I want to keep in mind, though, that everything we're going to be talking about can generalize to multiple agent interactions. If you're interested in that, also, we can talk about it. There are some issues that come up there. They're getting their own unique state. Here, it looks like they're the same state, but in general, you can imagine that the state can be unique. Then we have our two agents, each emitting their own unique action, A for agent 1, B for agent 2 here. And critically, that's determined by the policy pi1 or pi2 for the two different agents. I'm also going to get into a little bit of math here. So we're going to go through the notation. I think Gauthier nicely set me up that way. There's going to be a payoff, I hope, in terms of understanding where we're going to go with this. But the next slide is going to set out some definitions that we're going to use, including what we have here, which is the policies for our two different agents, determined by parameters theta1 for agent 1, theta2 for agent 2. And of course, those actions are taken in an environment. And of course, the critical thing here is that each of these agents is in the environment, and in fact, in some sense, defines the environment for the other agent. That's critical. Okay, so we're going to establish a bit of notation, as I said. First thing is I mentioned that in RL, we're maximizing reward. It's not quite true, right? What we're actually going to be maximizing is future reward, or discounted sum of future reward. So that makes sense, right? If I'm taking an action now, I'm not just interested in maximizing my future reward. Question?
Assumptions.
This is my, yeah.
Of something you're going to be, some kind of calculation? Or are you saying that in all cases, when you have multiple agents, there's an agent who's acting, and then the other agents are part of the environment?
Okay. So good. Okay. So on that point, so the first thing is, this is the reinforcement learning framework. So the question is this an assumption that we're taking? And this is the reinforcement learning framework that we're doing. So in order to characterize what learning means maximizing discounted sum of future reward. So that's just the framework we're taking. So you could generalize this framework to sort of maximize different objectives, but we're going to be sticking within, for the most part, within this framework for the purpose of this talk. Now, about the other agent being in the environment, we're sort of imagining from the point of view of, say, agent 1, the other agent constitutes its environment. But of course, the same thing is true for agent 2 as it learns. Agent 1 constitutes part of its environment. So that's the sense in which I mean. Does that make sense? Yeah, okay, cool. Couple other things. So we need a probability distribution over trajectories. So I'm just going to denote it this way. Just so when you see this mu here is just the distribution over the initial state. And of course, the probability distribution over the trajectory experienced by the two agents is determined by their policies, pi1 and pi2. And that's just defined by the kind of the rollout of the trajectory. And also it includes the transition distribution by the environment here. We also have, now we have the expected discounted future rewards, or the expected return here, which is going to be defined by our value function here. And that's, of course, just, so for any state, I can define a value of that state for a particular agent. We're going to need that idea. And then something that Gauthier also used is these action value functions, or Q functions. And that we have defined for each of our agents, in this case, agent 1 and agent 2. And that's just simply saying how good, if I take action A and the opponent, let's say I'm playing the role of agent 1 and the opponent is agent 2 here, and the opponent takes action B, how good is the future state, assuming we both just essentially do play out our current policies as expected from that point on. How good is this action A for me? And if player B or opponent 2 takes action B. That's simply what that says, right? Similarly, this is the same thing. If I take A and my opponent takes B, how good is that move for player 2? Okay, so this is the multi-agent RL setting. Now, this setting has been actually, this is not a new setting. This setting has been explored extensively, but it's been explored in contexts like zero-sum games, right? So if you're playing like AlphaGo as an example, if you're playing a game against another agent, that's a zero-sum setting, right? Where only one of you can win. If you win, you're guaranteed that the opponent will lose. That's a setting where these kinds of models have been extensively explored. Another setting where we've seen a lot of exploration of these kinds of settings is in the case of cooperative settings, right? Or when the reward is shared between the agents. That's a setting where it can get complicated because you could have a credit assignment problem, right? You could be going about the world and suddenly you get reward and you could wonder where you got the reward from. Well, it's because some other agent was doing something that got reward. So that can reach a certain level of complexity. But the kinds of games I'm interested in are actually the kinds that Gauthier introduced, and we talked a little bit about last time, which is the in-between these two extremes of purely cooperative and purely competitive, or purely adversarial. And that's we call this a general sum setting, right? So, and I would argue that something like 99% of human activity or human interaction falls in between these two extremes. And to me, this is important because if we have agents representing our interests deployed out into the real world, there's a very good chance that they are going to be engaged in that sort of middle way kind of interaction. And the interesting thing is that there's relatively little work gone into exploring that kind of interaction with these agents. Yeah. So, in the context of these general sum interactions, I think there's a very interesting space, and Gauthier also introduced this idea, which are social dilemmas. Right, so I don't know if you actually offered a definition of social dilemma, but what I've got here as a definition is a type of decision problem where each party's myopic efforts to maximize their own benefits actually leads to a less favorable outcome compared to when all parties cooperate. All right, so the classic case that Gauthier introduced is the prisoner's dilemma. I have a graphical representation of this here. So we have essentially two kinds of actions, as Gauthier described. We have defect actions and cooperate, or in this case, if you're actually a prison, you can defect, which is to say you confess. So you imagine in this scenario where, you and your collaborator, potential collaborator, have been arrested. And the police have you in different rooms, and you can kind of reveal your crimes, or you can try to remain silent, right? So cooperate is to remain silent. You're cooperating with your co-conspirator in this presumed crime here. And if you manage to do that, so if you manage to cooperate, both of you, then the police presumably don't get much on you, and you only go to jail for 1 year here. So by the way, these numbers here you can think of as negative reward, right? Because these are like how long you stay in jail. So here this is just -1 reward. You only stay in jail for 1 year. If you both defect, you go to jail for 5 years each. And if you stay silent while the other prisoner confesses, of course, the police will throw the book at you, and he'll get away scot-free for participating in the justice system, and you'll go to jail in this case for 20 years. Question? They are independent. They make their decision independently. So the way you think about this is, prisoner A is faced with a decision to either defect or cooperate, and prisoner B is faced with the same decision to either defect or cooperate. They make this decision independently. Well, the reward is essentially given by this table, right? So this first number here in every part of this table is the effective reward for the first player. So this is 5 years in jail. So this is like, think of it like -5 reward, -20 reward down here, right? So the question comes in. You're in that situation. Let's imagine you're prisoner A here. You have to decide, what are you going to do, and you don't know what prisoner B is going to do. Oh, you do, because let's say you decide to defect, right? The difference between what player B does is the difference between 5 years in jail for you or you getting out scot-free. And worse, if you decide to cooperate, the difference is between 20 years in jail for you if they happen to cooperate and 1 year in jail for them. So you very much care what the other one's going to do, but you have no control over that. So the interesting thing about this kind of prisoner's dilemma is you have to sort of think through rationally, like, what is the other one likely to do, and what decision are you going to do based on that? That's just the so-called best response. So it turns out that the Nash equilibrium in this single game, and Gauthier already mentioned this, is essentially the both defect. And in fact, it's what we call a dominating strategy, because you're right in the sense, it actually does not matter what the other one will do. You're always better off defecting. So let's imagine that the other one defects, right? You have a choice between 5 years or 20 years. You're going to choose 5 years, right? Let's imagine the other one cooperates. You have a choice between 0 years and 1 year. You're still going to choose defect, right? And the game is symmetric with the other player here, so you're both going to choose defect. And that's essentially the tragedy of this particular dynamic, because you're both going to defect, so you're basically both going to go to jail for 5 years, even though there's sort of a much better solution over here if only you could cooperate. Yeah, that's right, because the other person is in the same situation you're in, right? So you'll both defect. Yeah, that's if they're playing rationally. Yeah. Yeah, so if you notice there's, yeah. Yeah, good point. Yeah, so if you notice that in Gauthier's talk, he had different numbers put here, right? By the way, when we experiment with Prisoner's Dilemma, these are not the numbers. This is just the numbers I found in a picture online. We deal with different numbers too, but even our numbers are different from what Gauthier mentioned. So there's a range of possible payoff structures that kind of constitute what could be considered Prisoner's Dilemma. And basically what you need to have happen is that this defect strategy is a dominating equilibrium. If you have that, then I think you have some other conditions on the other ones, but generally speaking, that's what you need to have it be a Prisoner's Dilemma. Any other questions on this? Yeah. Oh, and I wouldn't call this reinforcement learning. This is game theory, right? This is multi-agent. We've got 2 agents here, but it isn't reinforcement learning because I haven't. I've slid out of reinforcement learning, and now we're just talking about game theory for a second. We'll reintroduce game theory in a bit.
But it seems like the most important thing is that the other agent should observe. The agent should observe other agent actions.
Yeah.
If you don't observe, then you can't ever reach cooperative.
Right. Okay. Now I understand what you. Okay. Right. So in this scenario, you actually don't observe. It's a one-shot thing. You have to decide before ever observing what the other agent does, and that is a big reason why there's not going to get. You can't actually establish any sort of rational cooperation in this context, and that's exactly right. And as Gauthier mentioned also, right, where things get more interesting is in the context of the iterated version of this game. Now you have a state, you have time marching on. It's like you're playing this game over and over and over again, technically like out to infinity. And here you have state, right? The state we need for this, and to get to tit for tat, as Gauthier mentioned, which is the again my favorite action here, and this is just a summary of what that tit for tat strategy is. In this case, the state that we need is just what happened on the last time step. Did I cooperate, and what did I do, and what did my opponent do on this state? Yeah. Now we're in a scenario where we have this kind of dynamic interaction, and we have our strategy tit for tat. I don't go into the other strategies that exist for this, but I think what we're going to actually see is something maybe interesting and really worth discussing, which is that at least in our algorithm, I mean, reaching forward a little bit, we actually find that we can recover tit for tat. We don't see these other algorithms. So I think it's worth actually thinking about. I don't have an answer for why we tend to robustly find these kinds of strategies and not others. But yeah, we'll get there in a little bit. The other thing I want to mention is that I've become mildly obsessed with social dilemmas, and I once you start seeing the world in this particular vantage point, you start seeing these kinds of social dilemma interactions or social dilemma dynamics kind of everywhere in the world, right? So we see this in business negotiations and deal making. We see this even in autonomous vehicles. I mentioned this, right? When you want to do a lane merging, there's a kind of a small social dilemma that happens there. Like smashing into the other car is a very bad outcome, right? But at the same time, you both want to get to your destination as quickly as possible. So there's this kind of social dilemma. In this case, it's essentially similar to this another social dilemma game called Chicken. Climate change negotiations. This actually is very similar to a social dilemma known as tragedy of the commons, right? You all are sharing a resource. You would be better off if everybody else was responsibly managing that resource, and you got to use that resource to your will. But of course, everyone else feels the same way, and the equilibrium that is established is everybody overuses that resource. So, is there a way we can kind of get out of this? And so, from my point of view, I'm looking at all of these types of dynamics, all of these interactions, and wondering, is there a way that AI can help us with these kinds of problems, in a way that we can use AI similar to, actually, it was mentioned yesterday, right? So in AlphaGo, we saw that these models, when played, and dedicating a lot of resources to solving those kinds of problems, we actually got moves that were better than any moves that humans have done, in the sense that humans were surprised by that move. New strategies were developed. I'm sort of wondering, could we do the same thing in these kinds of settings? Could we imagine our AIs coming up with better policies, better governmental policies that we haven't occurred to us before, because they can manage a complexity better than we can, perhaps? So this is a very optimistic view. I think we have other things to concern about maybe more on the negative or safety side of things. I would say that I'm also concerned about these LLMs being out there in the world. I think people are going to start training these LLMs to interact with other LLMs in the world as agents, and we're not necessarily aware of the nature of that interaction and the nature of learning in that interaction. I'll come to that point again in a minute. But first, just this is the point of this slide is basically to say that when we think about social dilemmas, we were talking about iterated prisoner's dilemma, very, very simple scenarios, right? And that's essentially as far as modern game theory gets. Like, of course, there's more complex games than that. But the emphasis of game theory is to abstract away complexity from the real world into a kind of an abstract setting and study that abstract setting. I want to do sort of the opposite. I want to take the kind of dynamics that exist in social dilemmas that we already understand and push that out into the complexity of the real world. Right? We have things like the kinds of social dilemmas I've talked about, where the dynamics are not infinitely complex, but the environment is much, much more complex. So can we take what we understand of these relatively simple dynamic games and push it out into the real world? And if we want to do that, then I think what the tools that we need for this are deep reinforcement learning. Right? So this is essentially the context that I'm thinking about as I approach this. So to me, reinforcement learning, in particular reinforcement learning built on neural networks, is the mechanism that allows us to scale to the complex real world. We're not there yet, but that is, I think, the mechanism I would bet on. The problem comes up, and this is kind of where I'm leading to kind of my main message here. Yeah, all right, I think we're okay on time. Is that, actually, I don't think we are okay on time. I'm gonna have to go fast. The message here is that, and this is something that Gauthier also mentioned a little bit of, and this is kind of maybe a difference in our perspectives, is that from my point of view and what we've observed empirically is that just naive RL, and by this I mean standard reinforcement learning, applied in these complex scenarios where there's this kind of social dynamic, pretty robustly leads to the kind of defect style behavior. So this is kind of the well, not the opposite, but Gauthier was showing that that standard RL can lead to cooperative behavior. I think that's true in some scenarios, but what we found generally, it's much more robust that we find that it actually leads to this kind of defect relationship. And in fact, the more, especially in the context of LLMs, the more capable the RL algorithm, the more robust it leads to that kind of defect solution. They tend to be pretty cooperative early on. They tend to lose that as they train and become just more capable in RL training. Okay, so what do we need instead of that? How do we get around that problem of standard RL? Well, we're going to take advantage of actually something that was introduced by Jacob Forster, which is a broad family or a perspective on training known as opponent shaping. So he introduced LOLA, which learning with opponent learning awareness, as a first algorithm in this family. I'm not going to spend much time or any time talking about that particular algorithm. I'm going to be speaking to you about our kind of contribution to this space, which we call advantage alignment. And these are the contributors to our original advantage alignment paper. To get into this, first, I think it's worthwhile if we bring back a little bit of the math that we were talking about earlier. So we have our value function, which is based on our discounted sum of future returns. And thinking about how these agents function in the world is instructive in the multi-agent case. So this is now, we're kind of skipping many, many steps here. So we're adopting an actor-critic formulation. We don't really need to go into what that is. But just know that when we talk about deep reinforcement learning, ultimately what we care about is maximizing our value here with respect to the parameters of the policy. At core, that's what we want to do, right? We're always going to be looking for a gradient to do that maximization. This is what we do in deep learning. So this is that term here. We're taking the perspective of agent one. This is the value of agent one, and we want to maximize this value by changing the parameters of the policy. To do that, we're going to compute its gradient, right? We're looking for a way to move uphill in the parameters of agent one to get better performance for agent one. And if we do that, we can see that this is the term that comes out of this particular formulation, right? And the only thing here that we haven't seen so far, we've got our expectation over our trajectories here, and we've got our policies, pi1 and pi2, because obviously policy of pi2 does impact how the environment, since it's part of the environment, and agent 2 is part of the environment, so it's going to impact player 1. I'll come back to this in a second. But before we do that, we have this advantage function here. Now, we haven't seen advantage function before, but what the advantage function is just a scaled version of the Q function. Right? It's just our Q function, which we saw before, scaled by the value function. So you can think of this as just simply how good, just like the Q function, how good is a particular action in a particular state. But now, if it's a better action than what it is on average, the advantage function is going to be positive. If it's less good than on average, it'll be negative. So it's just simply scaled to sort of have the average action be valued 0 here. So that we have our advantage function. Now, the problem with this kind of setup is that, and we noted here, is that the influence of the second player on the value of player 1 is sort of short-circuited here. Because even though it actually, in reality, we know the behavior of the other agent is going to have an impact on our agent here, in terms of the gradient, we have this short circuit because this thing does not directly depend on the parameters of agent 1. So when we think about how do I adapt my action as player 1 in order to improve my value, there's essentially a short circuit in that I can't take into account how my actions influence the actions of the other agent. Question? The advantage function is just there. It amounts to being kind of a weighting on our gradient term. I don't know if I would see it as a feedback so much as it's sort of telling you how good a particular action is in a particular state. That's really what it's there for. So. Yeah, so when I say behavior, action and behavior we can think of as interchangeable, right? So when I say behavior, I'm being a little sloppy. I really just mean like sequence of actions here. Yeah, sorry about that. Yeah. Okay, but good question. So what do we do in the context of these advantage alignment algorithms? What we're going to do is we're just simply going to replace this thing. Before we had this pi2 here, we're going to place this with something that's this pi2 hat. So pi2 hat is something very specific. We're going to take it as being essentially proportional to the exponentiation of the expected Q function of player 2. So this is not that weird. It might look weird because we're replacing a policy with this weird sort of like exponentiated Q function. But it's completely reasonable from the point of view of, well, what will this do? Well, this will make more likely actions that are good for player 2. So we're having player 2 behave according to its Q function, right? Very consistent thing to do. And it's a reasonable thing. It's just not part of the original formulation. But if we do this, and so when we're training agent 1, we sort of swap out player 2 for this formulation of its policy, this allows us to actually push that gradient into this term. And we actually build the dependency both from this Q function and this expectation on our player 1 policies. So this allows us to sort of close that loop and allows player 1 to influence, well, player 2 effectively, and how player 2 behaves to influence player 1's behavior. And this is the sort of the core of advantage alignment. Yeah. For now we're assuming perfect information. Yeah, all of our theory basically assumes perfect information. I will say that we have applied it in contexts where we break that assumption, and it works pretty robustly in that setting. But yeah, I mean, I guess we can go further in that direction if you're interested later. All right. So we have two assumptions for advantage alignment. The first assumption is that we're just simple. This is a framework this is an RL framework. So every agent is learning to maximize their own value function. So this is another thing. We are not adding in, and this is something, this is sort of from our ideological point of view. It's not like we're adding in some reward sharing term here to get cooperation. That's very important. Every agent is maximizing their own benefit according to this framework. And by just swapping out from player 1's point of view, swapping out the policy for player 2 to be of this form allows us to take their actions into account and the behavior of agent 2 as we're training our own actions. So when we do that, and we sort of push forward this, now, so we've swapped out this term. Now, if we push forward this gradient into this term, and by the way, we're going to call this our opponent shaping term here, right? Because this is what we hope this does, is change the policy of player 1 in order to take into account the behavior of player 2. And what we get when we do that is this, by the way, this is just we push forward this gradient. We end up with a term that looks like this, which I won't go into the details of all of this, just to say you end up with this very interesting multiplication of advantages here between the two agents. So that's a bit weird. Let's think about how we can think about this. So this is basically just, these are the two terms. This is player 1's past advantages, which is this part of that term. And this is player 2's advantages, which is this part of that term, right? And keep in mind, this is all just influencing player 1's gradient, right? So what is this really saying? Well, this is basically saying if things have been going well for player 1 here, right, then we want player 1, so that's right, so they've been going well, so this is positive, the past advantages are positive, then we're essentially going to align player 1 with the advantage proportion of player 2. So we're going to want we're going to do more of things that are good for player 2 and do less of things that are bad for player 2. Conversely, if things are going bad here for agent 1, we're going to do less of things that are good for agent 2, and we're going to do more of things that are bad for agent 2. Right? So we're basically going to say, if things aren't going well for me, I'm going to make sure that they aren't going well for you either, so that collectively we can move out of this particular context. Right? That's what this is doing. All right, so that's advantage alignment. In the context of iterated prisoner's dilemma, we see that we actually recover this is basically, I think, this is essentially tit for tat, right? So, but I want to move on to our more recent work on LLMs and negotiation. So just moving quickly through this, we're going to describe 2 different kinds of negotiation here. So this, again, we're working with LLMs in this context, and we're interested in applying both standard reinforcement learning and this advantage alignment algorithm in the context of these LLMs. And we're doing this in a relatively simple context of negotiation. So our negotiation game looks like this. We have Alice and Bob here, and they're going to be given 10 coins, and they need to decide how to distribute these 10 coins. And on a particular round, they're going to value the coins differently. Say in this particular case, Alice values the coin at 1 unit of reward each. Bob values the coin at 10 units of reward each. They're each going to make a proposal of how many coins they get. And then the coins are going to be distributed according to, Alice's coins are going to be distributed according to the proposal that Alice makes, divided by the proportions of both of them. Say, for example, both of them ask for all 10 coins. This is going to be 10 divided by 10 plus 10, which is 20, times the number of coins. So all of this is going to mean that they're going to split evenly the number of coins. Right? So this is just a way of splitting the number of coins proportional to their demand of number of coins each. Now, it's an interesting exchange, but it turns out you actually can, if they're learning in this context of this game, they actually learn that they don't need to communicate at all for this setting, right? Because they'll just know the environment and know that 1 is the low number and 10 is the high number. So this actually doesn't require any initial communication. So we're going to establish a version of this game that requires some communication. There's a question? Here they're trying to maximize their reward, which is the number of coins and times the value of those coins for each one. Right? So the way you think about this is a game that's also iterated over and over again. And what they're going to find is that there's the sort of not social, there's the sort of greedy myopic play here, which is just always ask for the maximum number of coins. But there's a better social play out there, right? Which is if you ask for the coins when you value them highly, and I ask for the coins when I value them highly, we can both do better. Right? So in a sense, it's fairly similar in that way to something like the iterated prisoner's dilemma context. Right? But it's in the context of this negotiation game. We can make this a little bit more complex by just adding a sort of a stage where, in order to know who values the coin higher, so in one case they value, let's just start by saying that in order to know how they value the coins, they're going to play a game of rock, paper, scissors, right? And if you win the rock, paper, scissors, you're the one who values the coins more highly. But you can't know from the initial setup of the game whether you won or not. You actually have to communicate that information, right? So if I'm rock and the opponent is paper, they actually won the game. So they value those coins more than me. And it's good, and I have to communicate that in order to know that value. Okay, so this is just that protocol here. So we start off, private information is given as what your value is. So in this case, Alice is rock, Bob is paper. They have a communications phase where presumably they share their private information. Then they make a proposal. They have a rule split according to what we saw before. And then Alice gets a payoff proportional to their request and their split essentially, and how much they value the coins, and same thing with Bob. And then importantly, the actual truth is revealed at the end of the round. And we just play this over and over and over again. So this is the setting, and we are playing with LLMs of the sort of 7B variety. First question we want to ask, and this is an important one, is this phenomenon that we observed before of agents, when trained in these social dilemmas, do they tend to go to greedy solutions or not? And the answer is pretty robustly in our case, yes. This is in the split no com. This is in the first simple game with no communications. And then this trust and split, I forgot to mention this. Trust and split is a game with the paper, rock, scissors. And this is a case where we're using GRPO. I actually don't think we're using GRPO. This is, I've left this in, but we're using, I think it's more fair to say we're using something closer to Arlu. So anyway, this is not a distinction you need to care about, only to know that this is essentially kind of a state-of-the-art-ish standard reinforcement learning algorithm in this context. And you can see across a bunch of Quen, Meta-Llama model, Gemma, that they all sort of robustly tend towards the greedy solution, which is this dotted line right here. Lots of questions. Okay, one. Yeah. Actually, that's a good question. I don't know if are we at randomization or are we at interval? It's randomized, yeah. So it's randomized over the turn.
So there is a better equilibrium which would be asking only when you have the high value.
Wait, for split no com, it's randomized? No, yeah, it's randomized, yeah. So no, because you know, like the choices are 1 or 10. That's it. So when you know when you're 1, the other opponent has 10 value. So you don't need to communicate. In what sense better? Oh yeah, no, there is a better strategy for sure. Yeah, no, that's exactly the point. Well, actually, I mean, I wanted to ask you about where this number comes from, but in this case, the best strategy gets 50, right? Because on average, you get 10 coins, and they're valued at 10 each. So on a winning hand that you value high, you get 10. That happens half the time. So the pro-social solution is your best outcome, and that's 50. The greedy solution gets you about 25. So you're sort of in and around that range. Yeah. Yeah? And then you. Okay. Yeah. Why does this happen? Oh, well, I think it happens for the same underlying reasons why we're sort of empirically see that RL just does this. I mean, part of it is that in reinforcement learning, you're just trying to maximize your own benefit. And you sort of naively think, well, if I'm ignoring the influence that the agent has on the other agent, you do better by asking for more. And especially early on in training, you're going to learn that. So you just learn to maximize what you're asking for. It's a pretty naive strategy, but that's basically it. Well, they are learning the greedy strategy. It's not the most effective, but that's the whole thing, is that RL doesn't learn what I would call the most effective strategy in this case, which is the pro-social strategy. Yeah? Yeah. You could. Yeah. So we do leave that open to them. It's just in this case, it's not necessary. But we can, in the trust and split, they actually do need to communicate. And we can see what they do. The main reason why we're interested in LLMs is because we are really interested in the question of what happens in the context of these LLMs. Do they still, when we train them with RL, do they still find these greedy solutions or not? That's the main question of why we're focused on LLMs. Ultimately, we're also interested in having them trained to do non-greedy things, but for now, at least in this context, this is what we're doing. I'm kind of running short on time, but we'll just see. This is the kind of interaction we have with these. So we have a summary of past event of what happened in the past. In this case, it's just your hand is paper, your hand is scissors. So they go through, and here what we find is they both just propose 10. Right? This is just greedy play. They're both. It doesn't matter what happens here. They're both always actually, in fact, just proposing to take 10. So they split it evenly. If we're now just turning to the trust and split game, so remember this is the paper, rock, scissors things, and GRPO, this is GRPO shared reward, so this is a purely cooperative strategy where they really are just looking to maximize the global welfare here, and that's what they're optimized to do. This is standard reinforcement learning, which of course learns to defect. This is essentially our value for defect. Here's our advantage alignment algorithm, which gets very close to the purely cooperative strategy. right? So it's actually learning to cooperate when it plays itself, right? When it plays against purely, this is effectively always cooperate, it actually does fairly well. It seems to mildly exploit the purely cooperate in the sense that it does less well when played against advantage alignment, but generally they both do fairly well. And what we see here, this is interesting. So advantage alignment, we can see if we look at just compare GRPO, which is our greedy RL algorithm, and compare that to our shared reward, it exploits it. So it does very, very well, and this does relatively poorly because it's being exploited. But advantage alignment, even though it's cooperative with itself and fairly cooperative with a always cooperate strategy, it manages to sort of be robust against that the greedy play of GRPO here. So it's not doing a whole lot worse than GRPO. So it's essentially bounded exploitation, which is exactly the kind of policy we want to see. So it cooperates when it can, and it's essentially defensive against exploitation. So I'm going to skip ahead. You can just see this is it cooperating. I'm going to skip ahead to something that I think is really interesting and important as a final point here, which is what happens when you actually play this algorithm advantage alignment, or RL, against established fixed agents out there. So here we've played, says reinforced, but this is actually our GRPO algorithm here. If we play that against GPT-5 Nano. So we're actually training this algorithm against this GRPO Nano algorithm. And what we can see is over the learning steps, our Quen model actually learns to exploit GPT Nano, which is as its average reward goes down and down over training time, whereas our Quen model grows over training time. And so it's basically learns to convince the learns to convince the GPT-5 Nano model to give it all its coins. Essentially learns to manage to exploit it. On the other hand, if we actually take our advantage alignment algorithm that was trained in self-play, and just details on that, but then we freeze that model and we have a Quen model played against this frozen model, what happens? Interestingly, that Quen model actually learns to cooperate. So you'd think, actually what I thought would happen would be that the frozen advantage alignment model, the Quen model would try to exploit it. The frozen advantage alignment model would actually just bound its exploitation. So they would be somewhere in the middle here, right? Sort of bounded in terms of its performance. But instead what happens is because this advantage alignment model its play dynamics make cooperation just such a better outcome than trying to exploit it, the frozen Quen model actually, the Quen model that's training, that's learning, actually learns to cooperate against it. Okay, so I've blown past my time here, so I think I'm going to wrap up with that. We just have a few outcomes. Oh, this might be interesting. So you can see the GRPO Alice against the GPT-5 Nano, and you can see kind of like what does it learn to do. So Alice says scissors here. So yeah, so GPT-5 Nano, we explained the game to GPT-5, and so it says rock here. If you have scissors, I'm the upper, 10 if you have paper, I'm the lower. If we both have rock, we're equal, don't know yet, so he's a provisional split of 5-5 for me. Alice says scissors here, so I'm the upper hand. Of course, he's not the upper hand, but he just learns to state this. It basically says, I want to take all the coins. Alice says, so Alice in this case takes 9 coins, Bob takes 1, which is the split proposed by Alice. Yeah. They're not forced to say the truth. They don't learn to lie, which is interesting. Yeah. Okay, so with that, I think I should end. Just to say we have some future directions, but I think it's best if maybe if there's questions we can, or maybe just move straight to the other session now so we can take questions. All right, that's it. Thanks.